In this video, I want to give you a brief overview of some of the mechanical features of exponential and logarithmic functions. Exponential functions and logarithmic functions appear quite often in physical models when you have a quantity that changes in relationship to the quantity itself. So the simplest example to think about, or the most common example to think about, is probably bacterial growth. When you have certain types of bacteria, they start out as, say, like a single cell composes that bacteria. And this single cell undergoes some biological transformations, and that cell splits into two cells that are identical to the previous cell, provided there's no mistakes or mutations or anything like that. So each cell, when it has enough nutrients, is able to split into two cells. And this is related to exponential functions because the way that this quantity changes depends on how many are there. So if I look at one bacterial cell and I watch it through its division process, I'll end up with two bacterial cells. So the change between the first stage and the second stage was that they doubled. But the interesting feature comes up if we look at this for a couple more stages. So if I take this, this process and I watch these two cells until they divide, what we'll see is that each one splits into two cells. So after two divisions, we have four cells. Now, this is not linear growth. This is different. This is what's called exponential growth. And the reason is that the rate of change, the number of new organisms we end up with, actually depends on the number that were there previously, because each one of these organisms is able to divide. So if we start to count these at a few different stages, we can fit them to a numerical pattern which actually corresponds to a certain exponential function. Okay, so let's look at one more stage, and then we'll have enough information to try to extract this pattern. So if we watch this for one more division, we should expect each one of these bacteria to split, to divide using whatever biologic processes they need to do that. So once they do that, I'm going to draw the graphic in a little bit lazily here. Say it's all these different cells, okay? And let's make a count of them. So at the first stage, if we started with just a single cell, after one division or one time step, this is going to split into two cells. Then after another time step, this would split into four cells. Okay? And then one more time step, or one more division, we have 1, 2, 3, 4, 5, 6, 7, 8 cells. Okay, so we've got the beginning of a mathematical sequence. We're looking at how this pattern of numbers corresponds to the number of bacteria that are going through these biological divisions. Okay? And the exponential function comes up if we want a way to predict or understand what's going on with this pattern with a mathematical operation. So what I want to do is I want to think of a function which has these outputs for the inputs of maybe 0, because we're starting out not waiting at all, just look at one cell to begin with, and then we wait for one division. Okay, so that's kind of like one time step. Maybe it takes an hour for this bacteria to divide, and then after 2 hours we end up with 4 bacteria. After 3 hours we end up with 8 bacteria. So if I search for a mathematical operation that can capture all of this information, it turns out that I can do that with an exponential function. Okay? And the exponential function that I would pick just for this simple pattern, this is kind of a simple example, I would think of this as being 2 to the, I'll use t as my argument. Okay? So my bacteria with the argument of t looks like 2 to the t. And let's make sure that this pattern actually matches up with the information that we have. If I call this first stage t equals 0, then 2 to the 0 is equal to 1. So this formula is going to predict the right thing at t equals 0. If I look at t equals 1, then 2 to the 1 is equal to 2. That works. If I look at 2 hours, or 2 time steps, whatever those happen to be, I get 2 squared, which is 4, so it still matches up there. And then finally, this last piece of data that we computed, or this last division we allowed, we have 2 to the 3, okay, which is 2 times 2 times 2, which is 8, so that also matches up. So with the pattern here, this formula, this exponential function, is able to match this doubling pattern. All right? So this is an example of a very, very special exponential function and a situation that it could be used to, you could possibly predict how many bacteria there would be, or you could ask how long it would take for the bacteria to multiply to a certain size. Okay? So this is kind of an example of an exponential function, and what I want to do now is just explore some of the mechanics of functions that look like this. So this was the special example that we looked at, but I want to show you this pattern in a little bit more generality, or this function in a little bit more generality. So I'm going to give you kind of a pattern for a generic exponential function, which I'm going to call a to the x. This is going to be our pattern for an exponential function. This a is called the base, and it's a constant when we're dealing with exponential functions. Okay? And then the x is the argument, and this is variable for exponential functions. This is different from a polynomial function because the argument, or the input, gets placed into the exponent position rather than the base position. And you'll see that the growth of these functions is actually drastically different than the growth of polynomials. So it's important to know that they're kind of different functions, different types of behavior. So if we're dealing with a function that has this structure, we can take advantage of the properties of exponents that we already know, the properties of powers that we already know, and they apply directly to this type of function. In addition, we might be interested in asking kind of inverse questions about functions like this, and this is where logarithmic functions come in. Okay? So if you had an equation that looked like this, x squared is equal to 4. If you wanted to solve that equation for x, you're going to need to perform an operation to isolate x, to get x by itself on one side. And we've seen that an operation that would do that for us is the square root operation. So when you're squaring something, you can take a square root. If you were cubing something, you could take a cube root, and that function would inverse that operation. But let's suppose that rather than a polynomial like this, or a power of our variable, we have an exponential function. And I just want to do some really, really simple examples to give you the idea. So let's look at maybe one of these relationships that we already have some knowledge about. Let's look at 2 to the x is equal to 8. So now, if I want to solve this equation for x, I want to get x by itself on one side of the equation. But that's really kind of difficult because I can't use an operation that depends on x. If I tried to use an x root, I wouldn't know how to compute that. Right? I wouldn't know how to evaluate the x root of x, or x root of 8, because I don't know what x is. So it turns out that when you have an exponential function and you're trying to uncover the value of the exponent, the operation that you need to perform is a logarithm. The logarithm is what we define as the inverse of these exponential functions. So if I have a base of 2 and I want to get rid of that to isolate this x, I'm going to use a logarithm to cancel it out. And it turns out that there are a whole family of logarithms, just like there are a whole family of exponential functions. Okay? I could have 2 to the x is equal to 8, or I can have 3 to the x is equal to 9. If I solve either of these equations for x, what that would mean would be I would want to find the value of x that makes the equation a true statement. Now this first example, okay, is one where we know the connection because of our previous work with this bacteria. We can say that 2 cubed is equal to 8. So that tells us that x should be equal to 3. That's what we expect is the solution to this equation, the value of x that makes it true. Okay? But here's a new situation, and we might not necessarily see the connection between 3 and 9 to know what power we can raise 3 by to get 9. If you can see it, great. But if you can't, that's the reason that we have logarithm operations. They give us a way to compute exponents in equations where we know all the other information. So in this situation, if we want to solve for x, what we do is apply a logarithm operation. And we have lots of different logarithms depending on what we happen to be doing. But here's the basic idea. We write the notation log base a for the logarithm base a. And this is the inverse function for a to the x. So if I think of this first formula as being f of x, this formula is f inverse of x. I'll give the argument of log a an x. Okay? And this function, just by definition, is supposed to cancel this operation out. So if we try to apply that algebraically to this situation, we would apply a log base 2, because 2 is the base in the equation, to both sides of the equation. And when we do that, that would solve for x. Okay? So if I apply a log base 2 to 2 to the x, and apply a log base 2 to 8, that's the right operation to get rid of this 2 in the base. Okay? So these two operations, 2 to the x and log base 2, those are inverse functions that cancel each other out perfectly. And this equation is going to reduce to x is equal to log base 2 of 8. So from our previous information, we can deduce that log base 2 of 8 should be equal to 3. Now, what I want to do is I want to give you kind of a phrase for you to understand what the log functions are doing, or what question they answer. So if you have log base a of b, the value that you should get is the power, should be equal to the power of a, which is equal to b. Okay, so when I do this, the power of a is all one thing. So it's a to the something is equal to b. So when you say log base a of b is equal to this thing, that's the same as saying, let's give a label to this. Let's say power of a, which is equal to b. Let's call that x. Okay? So the statement log a of b equals x is exactly the same. It's logically equivalent to a to the x is equal to b. Those are the same relationship. Okay? So here, in the second example, if we want to solve for x, we're going to apply a log base 3 to both sides of the equation. So if I apply a log base 3 to both sides of this equation, I'll be left with x on the left, because the log and the exponential cancel one another out. They're inverse functions. And on the right, we say log base 3 of 9. Okay? And the value here should be equal to the power that we would raise 3 to get 9. So what power do you raise 3 to get 9? If we think about that carefully, going through some of the easy things since we're doing this all in our heads, 3 times 3 is equal to 9. So the right power to raise 3 to get 9 would be 2. So in this second example, x is equal to 2. Let me separate these two examples with a vertical line. So you have these exponential functions which can be used to model situations where the growth of the material depends on how many things are there. Okay? And we have these logarithm operations which are invented or defined to help us solve equations where the unknown piece is actually appearing as an exponent. Right? So that's kind of a brief introduction to exponential and logarithm functions. Once you know what these things are, then you need to start to understand how they behave in algebraic environments, in different equation situations. So we'll look at these in a couple of different contexts to see how they behave.